previous lesson was all about capacitors connected together in parallel, and we said for any number of capacitors connected in parallel, the equivalent capacitance is greater than the largest single individual capacitor in that connection. Well, here we're going to talk about capacitors connected in series, and there's a different result of connecting capacitors in series. In fact, the equivalent capacitance for any number of capacitors connected in series is always less than the smallest individual capacitor in that network. And for capacitors connected in parallel, we noted that every capacitor has the exact same voltage. When capacitors are connected together in series, every plate has the exact same magnitude of charge. Now let's just show how we would diagram this. If we take the positive terminal of the battery and connect it to the positive terminal of one of these, and we take the negative terminal and connect to the negative of just one, and then we make connections like this, there's really only one pathway through which you can imagine getting from the positive terminal to the negative terminal of the battery, right? Go from positive through this capacitor, through this capacitor, through this capacitor, right? A series connection is really just one single loop in the circuit. So how do we diagram it? This is capacitor 1, 2, and 3. Then our circuit diagram might look like this. Here's our total voltage, or our battery voltage, and capacitors 1, 2, and 3. So notice, right, it's just one loop. Whereas capacitors connected in parallel have a circuit diagram in which there are three different loops. To get from positive to negative, we could take the far left loop, we could take the loop going through the middle capacitor, or a loop going through the other capacitor. Okay. So let's see why every capacitor has to have the same magnitude charge on every plate. So we take the positive terminal of the battery, and we've connected it to this uppermost plate. We take the negative terminal connected to the bottommost plate, capacitors number 1, 2, and 3. And then we connect capacitor 1 to 2 and capacitor 2 to 3. So electrons are conducted off of the top plate, making it, you guessed it, positively charged. And those electrons are conducted through the circuit and ultimately onto the bottom plate. And that's going to make it negatively charged. And that's it. Well, not really. See, all of this material, we'll highlight it in gray, this wire connecting capacitor 1 to 2 is a conductor. All the wires connecting 2 to 3 are conductor, and all the interior plates are conducting. So really, what happens is this conductor here, right? This is all one single conductor. Obviously, there's insulating material in this gap right here, but everything I circled is all conducting. So it gets charged by polarization. Any free electron in that conducting material would want to leave the bottom plate and move to the top plate. And so charge by polarization, or induced charge, appears on this plate. So now it's negative, leaving this plate lacking in electrons, so it's positive. And that same argument can be made for the other, for the other conducting plates. So because the internal plates are charged by polarization or charged by induction. That's why every single plate has the same magnitude of charge as any other if all of the capacitors are connected together in series. Okay, so the equation relating capacitance, charge, and voltage can be applied individually or in total. So let's see if we can figure out what we mean by the equivalent capacitance. Could we take a single battery and just connect it to one capacitor that stores the same amount of charge on its top plate as there is stored in this whole network, right? Okay, so the total voltage when multiplied by the equivalent capacitance gives us the total charge. But that total charge would be the same thing as Q1 or Q2 or Q3. So what we have is something called a voltage divider. The electric potential at this point is 1.5 volts, and if we choose to symbolize the circuit, so this point is ground, then we know the electric potential here is 0 volts. Now, what's the electric potential right here on the negative plate of Q3, or capacitor 3? 0 volts. What's the electric potential right here? Well, we don't know. What's the electric potential right here? We don't know. We know the electric potential here, there's a clear path to the positive terminal. So that would be 1.5 volts. So whatever the potential difference when we compare point A to B, or we compare point B to point C, or we compare point C to point D, the electric potential at point A minus the electric potential at point B, we can just say is the potential difference across capacitor number 1. And the electric potential at point B minus the electric potential at point C, we can describe that as the potential difference across capacitor 2. And likewise, there's a different potential difference across capacitor 3. But the one thing we know for sure is when we add all three of these potential differences together, V1 plus V2 plus V3, that's going to be VA minus VB plus VB minus VC plus VC minus VD. But that means the VB cancels out, the VC cancels out, and we just have VA minus VD. But that's nothing more than 1.5 volts minus 0 volts. In other words, it's the total voltage. So V total is equal to V1 plus V2 plus V3. But we can think of V total as Q total over C equivalent. And we can think of V1 as Q1 divided by C1. And V2 is Q2 divided by C2. We can apply the relationship between charge, capacitance, and voltage individually or in total, but there's no mixing and matching. We certainly couldn't say that the equivalent capacitance is the charge on capacitor number 1 divided by the potential difference across capacitor number 3. Nope, No mixing and matching allowed. So anyway, we can replace V3 with Q3 over C3. But this whole conversation about charging by polarization should convince you that all of these quantities are the same. So we can divide it all out, and we get 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Had we connected a 4th, 5th, and 6th, we just say so on. Okay, now don't get fooled mathematically into thinking this is the same thing as CEQ equals C1 plus C2 plus C3. If that's the case, I would love nothing more than to share a pizza with you. In fact, I'll be really generous when I share the pizza with you. I won't just give you half of the pizza. I'll give you a half of the pizza plus I'll give you 1/3 of the pizza, and therefore I'll be so generous that I will have given you 1/5 of the pizza. No, of course not. If I gave you half of the pizza plus 1/3 of the pizza, I would have given you much more than 1/5 of the pizza, right? I would have given you like 3/6 plus 2/6. In other words, I would have given you 5/6 of the pizza, and 5/6 is definitely much better than 1/5. You're better than that. I don't need to tell you that these don't mean the same thing, right? Okay, now, if it's the case of just having 2 capacitors, then we can simplify this expression. 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2, so we can make a common denominator and say this is the same thing as C2 over C1 C2 plus C1 over C1 C2. And that doesn't tell us what the equivalent capacitance is. That tells us what the inverse of the equivalent capacitance is. So for any 2 capacitors connected in series, the equivalent capacitance is equal to the product divided by the sum. Now what's that mean if we have 2 equivalent value capacitors together? Maybe a 100 microfarad capacitor connected to another 100 microfarad capacitor. Well, then we get 100 times 100 divided by 200. Let's knock off a couple zeros, and so we get 100 over 2, which gives us 50. Yeah, if you have any 2 capacitors of equivalent capacitance connected in series, CEQ is just equal to C over 2. Now does that mean if I have 3 identical capacitors all connected together, then the equivalent capacitance is equal to C over 3? Yeah, it does mean that. Okay, well what if I had 2 capacitors connected together, and this one has a capacitance of 1,000 picofarads, and this one has a capacitance of just 1 picofarad. What's the equivalent capacitance here? It would be 1 times 1,000 divided by 1,001, which is a number that's just, it's very nearly equal to 1. In fact, it's just slightly less than 1, which agrees with the statement that I said at the beginning of this lesson, that the equivalent capacitance is always less than the smallest individual capacitor in that combination. The equivalent capacitance in this case of a 1,000 picofarad and a 1 picofarad would be about 0.99 picofarads, which is a number that's smaller than the smallest individual. So let me test your understanding one last time here. If we take 3 capacitors and connect them all together in series, this one has a capacitance of 50 microfarads. This one has a capacitance of 10 microfarads, and the one in the middle has a capacitance of 3 microfarads. What's your best guess at the equivalent capacitance of this whole network? Well, it's certainly going to be something less than 3 microfarads. What exactly is it? Well, you have to use the formula. 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3 to find out, which isn't too challenging mathematically, and you can verify that this is indeed the case.